Okay, so this is for Monday 11/6. What we're going to do is start out, go to our materials in here. Let's do our prediction. Hopefully you guys can hear it in the virtual world. If you can't, you can watch it independently, like from your computer at home. Oh, hold on a sec.
So here I am up on a 12-foot ladder. I have two bocce balls. And what I'm going to do while I'm up here is I'm going to throw this bocce ball straight off to my side, while at the same time drop this bocce ball straight down. But the question is, which ball hits the ground first? The one that I throw off to my side, the one that I let drop straight down, or they both hit at the same time?
Were you guys able to hear that? I know I didn't have it projected, but when I do that, everything goes crazy. So, let's take a poll. Are you guys in the conference or are you?
No.
Okay. You what? I don't think you need to. So, let's take a poll in my virtual world. Let's see. Do you think the one that the guy is going to throw off to his side, or the one that he just drops, or do you think they'll hit together? Give me what you think. Okay. Okay. What do you think? Okay, what do you think, Connor? Okay. All right, let's see what our virtual people said. Nothing. No, we got Dalton in here. They will drop at the same time. AJ, I think the horizontal one. All right, while I'm glad you guys are all here, you have to be here within 10 minutes of it starting, or else we mark absent, and then you got to deal with that some other way. So I have to go back in and fix that. Okay, so let's see. Oh, I lost it. Where'd it go? Too many tabs. There we go.
When you say poll, I thought you meant like an actual poll, which is why I didn't write it in the chat.
It's okay. I know, I didn't switch up. So, think about what you thought, and let's see what happens.
So as you can see, they both hit the ground at the same time. Well, how'd this happen? Well, after I let both balls go, the only thing acting on them was gravity. Therefore, they both fell at the same rate. It didn't matter that I gave one ball some component of velocity in the horizontal direction. That's not affected by gravity whatsoever. Only motion in the vertical direction is affected by gravity. Therefore, I could throw the ball as hard as I wanted off to the side, and it would still hit the ground at the same time as the ball that I dropped straight.
Okay, so what he basically is saying, you guys could hear that okay, right? What he basically was saying is that both of those motions, both of those balls were in free fall. So even though he gave one a horizontal push, that doesn't change the downward direction. And its goal was to just reach the ground. So what we're going to do is we're going to pull up this PowerPoint. Actually, I don't like it this way, so let me pull it up this way. Okay, so this is here. My computer's very, very slow today. Wow. And it's not like it was sleeping all weekend. All right, so we're going to look at horizontal projectile motion. If you go off into college and you take physics again in college, you'll see that they'll give you different launch angles. You can shoot something up on an angle. We're just in this level, we just go horizontal. But the whole idea is that a projectile is an object that's launched and then follows a path due to gravity. We're going to make two assumptions. We're going to ignore air resistance, and then we're going to assume that our acceleration due to gravity is just downward. So really what we're going to do is we're just going to take all this information that we know about the x direction and all the information that we know about the y direction. We're going to have one object that's just going to follow a path. It's always going to look like a parabola, always, because gravity is going to pull it down as it's moving. And we're going to see how to approach it. And if you choose to follow the steps, it's easy. It's really going to be easy once you do a few practice ones. Okay? But if you just try to do it intuitively and just ignore the writing down of different things and the organizing of different things, then it's going to get trickier. So I highly suggest that you follow these little steps. All right. The idea is that the x direction and the y direction can be split up. Even though it's one object, we can analyze what's happening in the x direction, so horizontally, and then what's happening in the y direction. So here are some things that you're going to have to realize. We're going to find out that the acceleration in the x direction equals 0. So let's think back. What does that mean? If the acceleration is 0, what does that mean about the change in velocity? That's 0. So it means it's not going to speed up, it's not going to slow down because we're ignoring air resistance. So in real life, there would be a little bit of influence on it, but we're going to just take that away. And they do that in all, like even your freshman college physics. They look at things without air resistance. So this is great. So let's look at this equation that we're used to saying. VF equals VI plus AT, right? We're going to see that this is 0 because the acceleration is 0, right? So my velocity in the x direction is the same the whole way. So we're going to keep in mind that this is going to be our key equation for the horizontal direction. That's all you have to know. And again, you have that on your equation sheet. Here are some other things. If I launch something out this way and then it falls down like this, we're going to look at it moving this way, and then we're going to look at it this way. So we're going to look at this motion, then we're going to look at this motion. Well, guess what? In the y direction, your initial y velocity is 0, always. Because we're not going to do all these ones that are shot up on an angle. So that's fantastic. What else do we know about vertical motion? Free fall. What do we know? I can't see the chat, so if you're chatting. Awesome. Way to participate. These kids in class are on fire. You just can't hear them.
Oh, it's negative 9.8.
Thanks, Aunt.
Yeah.
Okay. So let's look at this too. We know that acceleration is a vector. We know velocity is a vector. We know displacement is a vector. All of these things are vectors. What's not a vector? Time. So our key is that the time on the left is going to be equal to the time on the right. So our time in the x direction is going to be equal to our time in the y direction, and that's what's going to link us together. That's what's going to link us together. So in other words, what you can do is you can plan out and you can organize all of your information. You got all your x stuff over here, you got all your y stuff over here. Once you look at that, you're going to see who has the most information. You solve for time, and then you can flip it to the other side and solve for whatever they're asking for. Okay, here are your steps. Best thing to do, make a little sketch, make a little label, sketch it out. If you're shooting something out of a cannon, if you're throwing something off a cliff, if you're flicking something off your desk, just sketch it real quick, label X's and Y's. Sort it out. Make a column for X, make a column for Y, and then you're just going to use your kinematic equations to solve for T on one side, then flip it over and use it on the other side too. You want to try one? All right. What was our first step? You look at your picture. You just said. So here's my house. Here's my baseball. So we know that Vx, because now you got to put your little subscripts in there for X and Y directions. So Vx, how fast do I throw it? 12 meters per second. It's going to follow this path till it hits the ground. Takes 1 second. Oh, it's asking after 1 second. How fast is it moving in the X direction? And how fast is it moving in the Y direction? So let's do this. Let's say here's all my X info, here's all my Y info. And I'm just going to stay in my habit of writing down all my variables. Remember, that's the key here. And I'm just going to put in for 1 second. And then what's my initial velocity in the Y? Nice. Vy. What's the time I'm looking? 1 second. Okay, so how fast is it moving after 1 second in the X direction? It's 12 meters per second. How about after 2 seconds? Good guess, but in the X. It's still 12. In the X direction, it's going the same speed the whole time. The whole time. So that's sort of a trick question on that side. But how can I find it out over here? I can use my VF equals VI plus GT.
Vx means the final velocity.
The Vx, if you saw on my little thing, VI in the X equals VF in the X. So if it's the same the whole way, I'm just going to shortcut it a little bit and call it Vx. So it's the velocity in the X direction. And we know that it's going to be the same. So we don't have to specify the VI and the VF in the X direction. Only because it's going to stay the same number the whole time, no matter what. So how fast is it going downward after 1 second? It starts at 0. 1 second later, it's going to be going How fast? You're negative 9.8. So VFY. Yeah, I should have had this little y here and this little y there. It's going to be negative 9.8 meters per second. Okay, so that's going to be our pattern on how to set them up. All right, so now we have a person who's skateboarding with a constant speed of 1.3 meters per second, releases a ball from a height of 1.25 meters. So we're really just looking at the ball, and it's not.
I know, it's not even skateboarding.
skateboarding.
And why is he dropping a ball while that's the stupidest thing I ever saw.
Okay, I have, okay, listen.
This is where our taxpayer money goes to.
So what? So she's not on a skateboard, fix it. There. Is that better?
Now the whole thing makes
it makes all better.
Now we can proceed.
I actually drop balls on my skateboard too. And then try to figure out the math.
Yes.
Can you go back to the last slide for just like a quick second?
Yes. There you go. Just don't touch each other's hoppers. Okay. The other class is much bigger, and like whenever they would get closer than 6 feet, I'd be like, ah! I'll try to think of something for you guys to be able to do so you can actually do something. Oh, but it won't be until after Thanksgiving, that's right.
We have any math lab for like the Pearson stuff?
We will, not tonight.
So there's no homework?
Well, it depends on how far we get. There'll probably be a couple in Khan Academy. You have to watch a video in Khan Academy.
Oh, that's it.
And then there's 4 practice problems.
on
On Khan Academy.
the Band-Aid.
I think so. All right, so are we set to look at this? Wow, it's going to be on the computer.
Yeah, but it doesn't seem to be wrong.
It should, because I'm recording a screencast. You just, yeah, and I'll put it into YouTube so you can speed it up, because if you don't, then you don't have the power to speed it up. Okay, so let's look here. I'm going to try and make this smaller so I have more room to write. There we go. All right, so your first, oh, I just took her off her skateboard. Let's leave her there. There we go. All right, so your first thing, you already have your little sketch. So basically, if you're just looking, don't even worry about the skateboard. If you're just looking at the path that the ball is taking, you know that we can divide things up into our X and Y. So that's your next step. Automatically, we know that our initial X and our final are going to be the same, so we can just call it VX. How fast is she moving?
1.3.
1.3, so that means the ball's moving that fast too. Delta X, we know A in the X direction is 0. You don't really even need to write it down, but it doesn't hurt. We know that our times are going to be linked. What's my initial velocity in the Y direction? Always 0. And I think, see how repetitious this is? And the more you do, the easier it'll be. What do you want to do now? How far is this ball going to drop vertically? You do. You're really close. It's going to fall downward, though.
Negative 1.2.
I know. Isn't that tricky? All right. So we got a whole lot of information. If we want to find out, it says part A, they want to find, let's go here. They want to find this. What the heck? And they want to find, no, they want to find, oh, they want to find out how far, right? So they want to find, this is just the way that they noted, and that's totally fine. We call it delta x, and we want to find delta y. And they give you a time. So the first time that they give you for part A is going to be 0.25 seconds. Okay, so even though they tell us how high above the ground it is, we don't have to use it. They want to know how far it has fallen. So let's put it all together. How are you going to find? Let's do the easy one. Let's do delta x. And then we can find delta y. What do you want to do? What's that equation for the x? What did that boil down to? The velocity in x is the change in x over time. So to solve for that, it's just delta x equals velocity times time. So how far did it get?
4.3 times.
Yep, crank it out there. Who's got a calculator nearby? Oh my goodness, the huffing and the puffing. Do you agree?
Yes, I do.
All right, so it only went very short, not even a meter. We know like how tall a meter is. So it didn't get very far after a quarter of a second. All right, find delta y.
VI T plus 0.5 GT squared.
Yep. And this boils down to like virtually nothing because our initial velocity is 0. So my delta y is just going to be 1/2 times, we're having some technical issues.
Did it just say like we can't handle any more drawing?
I don't know. I didn't really read it. I really didn't pay attention. Let's find out. 1/2. Yeah, I guess not. Maybe we need to. What the heck? This is fun. Okay, well, you guys just come up with that answer. You can plug those numbers in. 0.5 times negative 9.8 times 0.25 squared. Yeah, it's not going to let me write. Maybe over here. Nope. We're maxed out. So I think, can I just clear all? I don't know, maybe the next slide will let me write. Okay, does that make sense? All right, let me try and fix my speakers. Now, my virtual kids, it's probably going to be easier for you to watch this on your own computer. So our next slide, if you pulled up the PowerPoint and you're following along, this is an intro video. It is a Khan Academy. Once you watch it on your computer, then it'll show that you watched it. I'm showing it to my four in-person kids, so then I know that they watched it. These 4 practice problems, I'm going to work through one with you, and then the other 3 you got to get done by Wednesday night. Does that make sense? All right, so it's not letting me click. So you might want to mute us. Oh my gosh, I think my whole PowerPoint just kind of went wonky. So that's how I'm going to make sure that you guys are still with me.
Let's talk about how to handle a horizontally launched.
Oh, fantastic. I love playing with these speakers.
All the time, so I'm going to show you what that is in a minute.
All right, you guys ready? This video is going to show you an example problem, how they set it up. You can take notes in your notebook if you want now. If not, I would highly suggest you get some examples in your notebook, whether they were the ones we did in class or on here. That way you have a go-to. So if you want me to pause so you can get something out to write on, or you can write it out later. The enthusiasm is just through the roof.
Yes.
You can tell.
Yeah, I'm like just have the Khan Academy assignments up. Why did one say it's due tomorrow night and then the other one says Wednesday?
Oh, probably because I did it at like 11 o'clock last night, and I'll fix it though. Actually, no, it's the video.
Oh no, yeah, you're right. This one has a little play button. Okay.
Okay, so
Let's talk about how to handle a horizontally launched projectile problem. These, technically speaking, if you already know how to do projectile problems, there's nothing new, except that there's one aspect of these problems that people get stumped by all the time. So I'm going to show you what that is in a minute so that you don't fall into the same trap. What we mean by a horizontally launched projectile is any object that gets launched in a completely horizontal velocity to start with. So if something is launched off of a cliff, let's say, in this straight horizontal direction with no vertical component to start with, then it's a horizontally launched projectile. What could that be? I mean, a boring example is just a ball rolling off of the table. If you just roll the ball off of the table, then the velocity the ball has to start off with, if the table is flat and horizontal, the velocity of the ball initially would just be horizontal. So if the initial velocity of the object for a projectile is completely horizontal, then that object is a horizontally launched projectile. A more exciting example, people do crazy stuff. Let's say this person's going to cliff dive or base jump, and they're going to be like, whoa, let's do this. We're going to do this. They're pumped up. They're going to run, but they don't jump off the cliff. They just run straight off of the cliff because they're kind of nervous. Let's say they run off this cliff with 5 meters per second of initial velocity, straight off the cliff. And let's say they're completely crazy. Let's say this cliff is 30 meters tall. So that's like over 90 feet. That is kind of crazy. So 30 meters tall, they launch, they fly through the air. There's water down here, so they initially went this way, and they start to fall down, and they do something like, and then they splash into the water. Hopefully they don't hit any boats. Fish already looks like he got hit, he or she. All right, fish over here, person splashes in the water. We want to know, here's a question you might get asked, how far did this person go horizontally before striking the water? This is a classic problem. It's asked all the time, and if you were a cliff diver, I mean, don't try this at home, but if you were a professional cliff diver, you might want to know, for this cliff height and this speed, how fast do I have to run in order to avoid maybe the rocky, like, shore right here that you might want to avoid? There's this nasty, craggy cliff bottom here that you can't fall on. So how fast would I have to run in order to make it past that? Alright, so conceptually what's happening here, same thing that happens for any projectile problem, the horizontal direction is happening independently of the vertical direction. And what I mean by that is that the horizontal velocity evolves independent to the vertical velocity. Let me get the velocity of this clip. Let's say the vertical velocity, or the vertical direction is pink, horizontal direction is green. This vertical velocity is going to be changing, but this horizontal velocity is just going to remain the same. These do not influence each other. In other words, this horizontal velocity started at 5. The person's always going to have 5 meters per second of horizontal velocity. This horizontal velocity is always going to be 5 meters per second the whole trip, assuming this person really is a freely flying projectile. Assuming that there was no jetpack that propelled them forward or no air resistance, this person's always going to have 5 meters per second of horizontal velocity up until the point right when they splash into the water, and then at that point, there's forces from the water that influence this acceleration in various ways that we're not going to consider. How about vertically? Vertically, this person starts with no initial velocity. This person just ran horizontally straight off the cliff, and then they start to gain velocity. So they're going to gain vertical velocity downward, and maybe more vertical velocity because gravity keeps pulling, and then even more. This might go off the screen, but it's going to be really big. So a lot of vertical velocity. This should keep getting bigger and bigger and bigger because gravity is influencing this vertical direction, but not the horizontal direction. So how do we solve this with math? Let's write down what we know. What we know is that horizontally, this person started off with an initial velocity. V initial in the x, I could have wrote I for initial, but I wrote 0 for V not in the x. Still means initial velocity is 5 meters per second. And we don't know anything else in the x direction. You might think 30 meters is the displacement in the x direction, but that's a vertical distance. It's not telling us anything about this horizontal distance. Horizontal distance or displacement is what we want to know. This horizontal displacement in the x direction.
So he calls it d, but we call it delta x.
Declare our ignorance. Write that here. We don't know how to find it, but we want to know that we do want to find it, so we'll write it there. How about in the y direction? What do we know? We know that all right, now we can use this 30. You might want to say that delta y is positive 30, but you would be wrong. The reason is this person fell downward 30 meters. Think about it. They started at the top of the cliff, ended at the bottom of the cliff. It means this person is going to end up below where they started, 30 meters below where they started. So this has to be negative 30 meters for the displacement. Assuming you're treating downward as negative, which is typically the convention chosen. The downward is negative and leftward is negative. So if you choose downward as negative, this has to be a negative displacement. What else do we know vertically? Well, for a freely flying object, we know that the acceleration vertically is always going to be negative 9.8 meters per second squared, assuming downward is negative. Now here's the point where people get stumped. Here's the part where people make a mistake. They want to say that the initial velocity in the y direction is 5 meters per second. I mean, people are just
what is it? We know it's not
5 meters per second.
0.
Here because that's the velocity that you were given. But this was a horizontal velocity. So this is called horizontally launched projectile motion, not vertically launched projectile motion. So think about it. The initial velocity in the vertical direction here was 0. There was no initial vertical velocity. This person was not launched vertically up or vertically down. This person was just launched straight horizontally. So the initial velocity in the vertical direction is just 0. People don't like that. They're like, hold on a minute. They're like, this person's going to start gaining, right? This person's going to start gaining velocity right when they leave the cliff. This starts getting bigger and bigger and bigger in the downward direction. But that's after you leave the cliff. We're talking about right as you leave the cliff. That moment you left the cliff, there was only horizontal velocity, which means you started with no initial vertical velocity. So this is the part people get confused by because this is not given to you explicitly in the problem. The problem won't say, find the distance for a cliff diver, assuming the initial velocity in the y direction was 0. Now they're just going to say, cliff diver ran horizontally off of the cliff, find this stuff. And you're just going to have to know that, okay, if I run off of a cliff horizontally, or something gets shot horizontally, that means there was no vertical velocity to start with. I'm going to plug this initial velocity in the y direction is 0. So that's the trick. Don't fall for it. Now you know how to deal with it. So we want to solve for displacement in the x direction. Look how many variables we know in the y direction. We know all of this. This is good. But we can't use this to solve directly for displacement in the x direction. We need to use this to solve for the time, because the time is going to be the same for the x direction and the y direction. Once I find the time, I can plug back in over here, because think about it, the time it takes for this trip is going to be the time it takes for this trip. It doesn't matter whether I call it the x direction or y direction, time is the same for both the directions. In other words, the time it takes for this displacement of negative 30 is going to be the time it takes for this displacement of whatever this is that we're going to find. So let's solve for the time. Now, how will we do that? Think about it. We know the displacement, we know the acceleration, we know the initial velocity, and we know the time. Note that we don't know the final velocity, and we're not asked to find the final velocity. We don't want to know it. So let's use a formula that doesn't involve the final velocity, and that would look like this. So if we use delta y equals the initial in the y direction times time plus 1/2 acceleration in the y direction times time squared. All right, now we can plug in values. My displacement in the y direction is negative 30. My initial velocity in the y direction is 0. This is where it would happen. This is where the mistake would happen. People would just really want to plug that 5 in over here, but don't do it. It's a trap. So 0 times t is just 0. So that whole term is 0. Plus 1/2. The acceleration is negative 9.8 meters per second squared. And then times t squared. All right, now we can solve for t. I'm going to solve for t, and then I have to take the square root of both sides because it's t squared. And what would I get? I'd have to multiply both sides by 2. So I get negative 30 meters times 2. And then I have to divide both sides by negative 9.8 meters per second squared equals, notice if you would have forgot this negative up here for negative 30, you would have come down here, this would be a positive up top, you would have had a negative on the bottom, you would have plugged this in, you would have tried to take a square root of a negative number, your calculator would have been all like, I don't know what that means, and you would have been like, messed up, so you'd start coming back here probably and be like, let's just make stuff positive and see if that works.
Yeah, so seriously, kids, if you get to a point where you get a negative under your square root sign, you know that something's wrong. Don't just ignore it, but go back in and check it out.
2.47 seconds, actually a long time. Might seem like you're falling for a long time sometimes when you're like jumping off the table, jumping off the trampoline. That's usually like a fraction of a second. This is actually a long time. 2.5 seconds of free fall is a long time. So if you take this, that's how long it took to displace by 30 meters vertically. That's going to be how long it took to displace this horizontal direction. We can use the same formula. Say that, well, if delta x equals the initial in the x direction, I'm just using the same formula but in the x direction. Plus 1/2 ax t squared. So the same formula as this, just in the x direction.
Well, what happens to this?
Delta x is just dx. We already gave that a name, so let's just call this dx.
Okay, if you use this equation over here on the x, what happens? What goes away? Does this term go away? Does this term go away? Why?
Because there's no negative 9.8, right?
There's no acceleration. The acceleration is 0. So you're going to see that you use the same equation. It's just on this side, this term goes away. In this side, this term goes away.
All of that.
This whole term right here, because you're multiplying 1/2 times 0 times t squared. Anything times 0 is 0, and you're left with that basic velocity is displacement over time. Sounds like a plan.
Let's scooch this equation over here. dx is delta x. That equals the initial velocity in the x direction. That's 5. All right, this is really 5 now. In the x direction, the initial velocity really was 5 meters per second. How about the initial time, or sorry, the time, there's no initial time. The time here was 2.47 seconds. This was the time interval, the time between when the person jumped off the cliff and when the person splashed in the water was 2.4, let me erase this, 2.47 seconds. So 2.47 seconds.
And we are almost out of time.
To 0. Remember, there's nothing compelling this person to start.
So I'm going to run this video through there. It's on Khan Academy.
There's no air resistance. There's no reason this person's going to accelerate horizontally. They maintain this.
Let me just pause because we're the bell's going to ring soon. There are 4 practice problems that I want you to get done by Wednesday night so that when we come in Thursday, we can do problem solving together. Any questions on that? Let me check the chat. You do not need to watch the video again. You guys are already counted. And then you guys out here in virtual land for practice. Whoops, my computer's wacko. Problems in Khan by Wednesday night. Also, if you start and you are just completely lost, there are office hours on Wednesday.
Oh, yeah. Can you submit the lab again if you already submitted it?
You should be able
Like
to.
I submitted on Friday. Can I do it? I submit it again with the request for revisions.
Oh, yeah.
Last thing.
Sure.
So, like,
Nick, I'll be right with you.
the velocity of the hopper before it hits the table is the same thing. It's just the negative version of the normal velocity.
Of the initial.
Alright.
Yeah,
I'll submit it later.
it's fine. Nick, what's up? Oh, hold on one second.